In this video, I'll show you how to run analysis of covariance, that's ANCOVA, in SPSS. ANCOVA is a way to equate groups on one or more variables and for increasing the power of a statistical test. Roughly speaking, ANCOVA allows you to remove the effect of a covariate. ANCOVA basically tests whether certain variables, other than the covariate, have an effect on the dependent variable after removing the variance accounted for by the covariate. There are some strict assumptions about the use of ANCOVA. All assumptions applying to ANOVA are required, like random samples. In addition, the covariate must have a reasonable correlation with the dependent variable. That means there's a linear relationship between the covariate and the independent variable. The ANCOVA must also satisfy an additional assumption, that of homogeneous regression slopes. That means the slopes of the regression lines representing the relationship between the covariant and dependent variable are similar. I'm running some research. The randomly selected group of 24 students were randomly assigned to 4 methods. A pretest was administered to all students, then a semester-long class was taught. One method was taught to each group of 6 students. Following the research, we administered a post-test. I can't run a one-way ANOVA because I suspect the pretest may have had some influence on the results. The null hypothesis for the ANCOVA is that the means are equal for all 4 of my groups. I entered my data into a worksheet. On the values column in variable view, I entered 1 through 4 for my 4 teaching methods. I also have 2 scale variables for pre- and post-test results. Before I run ANCOVA, I'm going to run a test for normality. Click Analyze. Descriptive Statistics. Explore. Place the pretest and post-test into the dependent list box. For statistics, I want descriptives. Click Continue, choose Plots. Check histogram and normality plots, continue, then OK. The skewness and kurtosis are very small for both pretest and post-test. But what we're interested in are these tests for normality. In these tests, we do not want to reject the null. All of our p-values are very large for the KS and Shapiro-Wilk, so we can't reject the null hypothesis. We can continue with ANCOVA. Scrolling down, histograms and QQ plots confirm the finding that we have an approximately normal distribution. However, before we can actually run the ANCOVA, we must also check the assumption for homogeneity of regression slopes. Here's how to do that. Click Analyze, select General Linear Model, click Univariate, click Post-Test, then click the right arrow to move it to the dependent variable box. Click Methodology, then click the right arrow to move that to Fixed Factor. Click Pretest and move that to Covariate. Click Model. Click Build Terms. You want to make sure the interaction is showing in the box under Type. Click Methodology, then click the arrow to move it to the Model panel. Move Pretest to the same panel, click Methodology again, hold down the Control key, then click Pretest. Move that combination over to the right, then click Continue. Click OK. If we look at the methodology pretest, the p-value is 0.131. That's greater than 0.05. So we fail to reject the null, that there is no interaction. Our regression slopes are homogeneous, so we can continue with ANCOVA. Let's run the test. Click Analyze, General Linear Model, Univariate. Click Reset at the bottom of the window. That clears the data from the test we just ran. Click Post-Test, move it to the Dependent Variable box. Click Methodology, move it to Fixed Factors. Click Pretest, move it to Covariates. Click Model. Click Build Terms. Click Methodology, move it to the Model panel. Click Pretest, and move that to the Model panel. Click Continue. Click EM Means. Move Methodology over to Display Means. We want to compare main effects. Click Continue. In Options, we want Descriptive Statistics and Homogeneity Tests. Click Continue, then OK. A quick look at the means tells us they look different, but we don't know at this point whether those differences are significant. Levene's test indicates the assumption of equality of variances has been violated. That's because 0.002 is less than the alpha level of 0.05. At this point we should stop and consider running a non-parametric analysis. However, let's say for argument's sake this was not rejected. Next I'll show you how to read the other results. Let's say instead of 0.002 you got 0.655. As this is bigger than 0.05, you would not reject the null hypothesis, and you can continue reading the ANCOVA output. Here are our main results. Did the 4 teaching methods result in significantly different scores than the post-test? The p-value in the methodology row is 0.005. That's smaller than 0.05, so we can reject the null of equal means for the different teaching methods. This result is after we have controlled for the pre-test. Another important finding is found in the pre-test covariate row. This tells us whether there's an association between the post-test and the pre-test when the methodology is controlled for. The significance here is 0.019, therefore that is also a significant result. Now that we know we have overall significance, let's find which of the teaching methods are significantly different. This table tells us that traditional teaching is different from all of the other methods. However, there's no significant difference between all of the other pairs. We can reject the null hypothesis that mean 1 and mean 2, mean 1 and mean 3, and mean 1 and mean 4 are equal. I hope you found the video helpful. Please take a moment to subscribe to my channel, and I'll see you in the next video.